Good evening and welcome all. I expect all of you to keep your cameras on. If anyone facing any problems, please inform through the help and support group. If anyone is facing any problem, not able to turn on the cameras, anything, okay, you should inform through the help and support group. What I expect and what liberties I provide is you have to be present here, keep your camera on. You can be doing whatever you want. Like if you want to eat, you can be eating something. If you are drinking, you can drink. Okay, there are no obstructions to that. But if you have to leave the class, suppose you have to leave the class, you have to go somewhere, you have urgency. So don't just leave like that. Okay. Don't just leave like that.
Can you say them?
You just
Can you
inform
say it
and
again?
yeah.
And just
So if you have to leave the class somewhere in between, inform and then leave. Okay. So keep your camera on. Okay. Anyone having any issues while not being able to turn on the camera? So please inform through the help and support group. Okay. Aryan, thank you. Okay, so in the last class, we had done about refraction of light. We had done refraction through a glass slab. Okay. So what are the factors on which the refraction through glass slab depends? Yes, anyone remembers the factors on which the refraction through glass slab depend? That is lateral displacement.
So
In the
refract.
last, refractive index and okay, in the last class we had about the glass slab. Okay, and in the glass slab we observed that there is refraction at two points. You'll find refraction at 2 points. If you have an oblique ray of light falling on the surface, so suppose if you have an oblique ray of light falling on the surface, so let's say it's making a certain angle with the normal. This is our normal. So the ray was expected to be moving like this. It was expected to be moving in the straight line, but due to refraction of light, it will suffer a number of bending. So this is what was expected. This is the path of the incident beam of light. Okay. Now, at this first interface, due to refraction, it bends towards the normal because here you have air being a rarer medium and glass being a denser medium. So this is your glass, which is denser medium. So the ray of light will bend towards the normal. Here the ray of light bends towards the normal here. Now at this point, again we'll draw the normal. So let's say this is our normal here at this point. So at this point you have the normal. Then the ray of light from here, again it will suffer a refraction. But now it's moving from glass to air, from a denser medium to a rarer medium. So it will bend away from the normal. So it will bend away, something like this, so that the incident ray and emergent ray both are parallel to each other. So it would be something like this. You have incident ray and finally you have the emergent ray. This is our incident ray. This is our angle of incidence, angle of refraction. This is also angle of refraction. This is angle of emergence, and the perpendicular distance between them. The perpendicular distance between these two incident ray and the emergent ray is called as the lateral displacement D. So first of all, what all things we can conclude from here? We had included that angle of incidence is equal to angle of refraction. So I is equals to R. Sorry, not R. Angle of incidence is equal to angle of emergence, not R. Angle I is equal to angle E. And you have lateral displacement D. It depends on following factors. You have lateral displacement D. So the lateral displacement D depends upon refractive index of the material. It depends on thickness of the material. Also, it depends upon angle of incidence. It depends upon angle of incidence, and it also depends on color of light, that is wavelength. Color of light, that is wavelength. So these are the factors on which the lateral displacement depends. Here we observed that the incident ray is parallel to the emergent ray because the opposite faces are parallel to each other. Here we have the opposite faces parallel to each other, and hence you will have the incident ray and the emergent ray parallel to each other. Now, what if the surfaces are not parallel? That is, let's take up the lenses. So here we have lenses,
Sir,
and
could you
there
show, sir? I'm writing.
this one.
Yes, sir.
Okay. Okay. So let's move to the lenses. The next one is lenses here. So we have two types of lenses. The lenses are either concave or convex. You either have a concave lens or a convex lens. So see how we know whether a given lens is a concave lens or a convex lens. Okay, so I'm making here a lens. See, the convex lens is thicker in the middle and thinner at the edges. Okay. So you have here, see, just 1 minute. Let me complete it. So you can have a lens something like this, which is thicker in the middle. Okay. So this one, and you can have a lens something like this also, which will be thicker in the middle and thinner at the edges like this. So these are the two lenses which we have to study. There are other lenses also. Apart from them, you will find out some other lenses. So this one is our concave lens. It's thicker in the middle. You can see it's a cave-like structure over here. So this is a concave lens, and this one is a convex lens. So in the convex lens, you have thicker centers. The center is thick and it's thin at the edges. Now, if you do it like this, suppose if I complete a sphere. Okay. So if I complete a sphere, I can draw a circle with this portion, and with this portion also I can draw a circle. So in this way, these lenses are called as spherical lenses, because here you have two refracting surfaces. Okay. And these two refracting surfaces, they are spherical in shape. The two refracting surfaces are spherical in shape, and hence we call them as the spherical lenses. Now, to study their properties, see how the refraction occurs. I'll explain the refraction with one of the lenses, and then we will interpret in the similar way for the other. Okay. So for instance, currently I consider just one lens. Let's have our convex lens and try to see how the image formation occurs through it. So let's say a convex lens we can take. Just no, I just want a convex lens. Okay, this one. See, you have this convex lens, the one which is thicker in the middle. This is our convex lens. Okay. So let's try to study the image formation through this convex lens. So for this, a point is defined well inside this. That point we call as the optic center. So you join these two points from top to bottom. You join from here top to the bottom of the lens, and through its middle also you draw a line. So through its middle also you draw a line. The point of intersection between them, this is the point of intersection. This point we call as the optic center, represented by O. So O is the optic center. O is optic center. Got it? Now see how the refraction occurs. So when a ray of light falls on this surface, you have a ray of light that falls over here on this surface. So here refraction will occur at the first surface. That means when ray of light enters through this surface, there it will perform refraction. It will have refraction, bending of light will occur. Now to study the bending of light, in which direction will it bend, we need to draw the normal. And to draw the normal, we take its center of curvature. Let's say this be the center of curvature. I'm supposing it to be the center of curvature. And I can draw, okay. So this would, if I join from here to here, it would be the normal. So this is our normal. Now, in which direction do you think that should the light bend? The ray of light is traveling from air to glass.
Away from normal.
Away from
So-
normal or towards the normal? It is entering from
Towards the normal side.
towards the normal. So it is entering from air to glass, and hence the ray of light should bend towards the normal. So see, this was the direction in which it was going, and it must bend towards the normal. So it must bend something like this. Okay. So it must bend something like this, and hence by bending like this, it reaches the second surface. Okay. So, okay, I'm not drawing the complete ray. I'm just drawing a part of the ray so that it reaches the next surface. So now it has reached the second surface. At the second surface here, now the center of curvature for this surface will lie to the other side. It will lie somewhere here. And now we need to draw the normal like this. Okay. So something like this. You have, it's like this. And hence it must bend, the ray of light must bend away from the normal. See, this was the direction in which it was going, and above this you have the normal. So it must bend away from the normal, and hence it must go still down like this somewhere. It must go still down and touch the principal axis somewhere. Once more I am explaining. Okay, anyone having any doubts?
So once again, can you say?
Okay, okay. So basically, we are looking here that when a ray of light enters a lens, so there are two times when the refraction occurs. First, refraction occurs when the ray of light enters the lens, and secondly, the ray of light when it leaves the lens, just like the glass lens. But here the surfaces are spherical; they are not rectangular. Okay. So here you have the surfaces are rectangular, not rectangular, they are spherical, and hence you find the bending of light towards the north and away from the north. Same way, finally the ray of light, it bends more and more, so it touches the principal axis. Somewhere it will touch the principal axis. If you have another ray of light here, take another ray of light, it will suffer two refractions, bend here, and finally it will reach here. How we have drawn the normal? That is joining the center of curvature to the point of incidence. So we can summarize a few rules to make the ray diagram. What rules we talk of here is that see, if you have a ray of light moving parallel to the principal axis. So let's first draw our principal axis, mark the optic center. So the point of incidence here, the point of intersection is your optic center O. If you have a ray of light, so let's say that this is a ray of light which is passing parallel to the principal axis. So this ray of light which passes parallel to the principal axis, it bend towards the normal. So it will bend towards the normal like this. You have a ray of light which again passes parallel to the principal axis. So this ray of light also bends towards the normal. Okay. So in this way, you will have the rays of light bending towards the normal and they meet at a common point. So the common point where they meet is the focus. Is it understood to everyone?
Yes, sir.
Okay. So okay. So here we observe if we have a ray of light parallel to the principal axis, it bends towards the normal. And all the rays of light which are parallel to the principal axis, they meet at a common point, and we call this point as focus. So what do you think will happen to the ray of light which comes from the other side? Suppose you have a ray of light which comes from the other side, like this. If it comes from like this, so will there be another focus on this side?
Yes, sir, because it has two sides. It's a
Yeah,
length.
yeah, it's a lens and both the sides are similar. So on this side also you will have a focus. Okay. So in a lens, you will have two focus, one on the left side, one on the right side. So for the ray of light which comes from the left, they will find their focus on the right. For the rays of light which come from the right, they will find their focus on the left. Okay. So for a lens, we draw these points. See, just one minute. So for this lens, what are the points that we take for consideration? So, okay, see the points. I told you about optic center. You know the optic center is the point which is just the middle of the lens. So that is your optic center. You will find a focus on the left side, a focus on the right side. Okay. And both the focus will be to the same distance from the optic center. So from the optic center, the focus or the focal length will be the same. Okay. So we say this focus to be f1 and this focus to be f2. The focus we call as f1 and f2. We take another point which we call as the double of focal length. We do not call it as the center of curvature. So you have some other point here which we call as 2f1, which is double of the focal length. And on this side also you have double of the focal length which we call as 2f2. Okay. So these are the points. Of course, you know this is your you have the principal axis. Aryan, are you there?
Yes, sir.
Okay, I couldn't see you. Now I can see. So see, one of the rule we have seen, if we have a ray of light passing parallel to principal axis, right here we did, we have a ray of light passing parallel to the principal axis. So this ray of light bend towards the knob. It passes through the focus, and we show refraction from this vertical line. The vertical line which we have drawn passing through the optic center, we show the bending from this point, not at the first and not at the second. Okay, because it's very difficult to show two refractions in this small lens. Okay, the second rule is that if you have a ray of light passing through optic center, So if you take any ray of light passing through optic center, the ray of light will pass undeviated. So you have here a ray of light passing through optic center. It will not suffer any refraction. There will not be any refraction to a ray of light which passes through the optic center. So here we have taken this ray of light passing through optic center, no refraction. What do you think will happen to a ray of light which passes along the principal axis?
Continues on the principal axis.
Yes?
Continues to be on the principal axis.
Yeah, it will continue to be along the principal axis as it is passing through the optic center. Okay. So since it passes through the optic center, so it will not show any deviation and it will pass undeviated. Okay. So this is, see, all these things we have studied about the convex lens. In the similar way, we have these words with the concave lens also with a little bit of differences. The terms are the same, but there are little bit differences in their properties. Okay. So here we'll first study about the convex lens. We will see the image formations by convex lenses. Okay. So here now a convex lens is the lens which always forms a real, which can form a real image. So we have the ability of a convex lens forms real image, but not always. We will see just like the mirrors, the concave mirror could form real images, but not always. In the similar way, we will also observe that a convex lens, it forms real images, but not always. Okay. And I hope all of us know what is a real image. Dharya, what is a real image?
So an image that can be captured on a screen.
Yeah, the image that can be captured or obtained on a screen is the real image. The image which cannot be obtained on a screen will be a virtual image. So if you try to focus a distant object, if you have a distant object and try to focus through a convex lens, so what we will observe here, we will observe all the light rays will come parallel to each other. Okay. So here we have another lens. And let's say if you have object at infinity. So if the object is located at infinity, then all the rays of light which will fall on this lens, they will be parallel to each other. Okay. So again, we will observe the rays of light coming parallel. Here you say, I have taken one object. Here I have taken another ray of light. So a number of rays of light, they come from the object. But since the object is very far off, so we observe that all the rays of light, they are parallel to each other. So this only happens when the ray of light is very far off as compared with the size and focal length of the lens. If you have the size of length as very small and all the light object is very far off. So in that case, we will consider all the light rays to be parallel to each other. And hence all these light rays which are coming parallel to the principal axis after reflection, they all meet at a common point on the principal axis. So the point where all of them meet is the focus. So in the first diagram, we have when the object is placed at infinity. See? If the object is placed at infinity, all the light rays come parallel to the principal axis, and after reflection, they meet at a common point which we call focus. So they meet at focus. Anyone having any doubt? So this we have also observed when we have played with these convex lenses. In the you must have tried to burn a piece of paper with the help of a lens and sun. Have you ever tried to focus all the sun's light at a common point? Anyone who has used a convex lens for this purpose or a magnifying glass?
No, sir.
None of you.
Yes, sir.
Yes. So I think you should, if you find a magnifying glass, so you should try to use that magnifying glass. Use that magnifying glass to burn a piece of paper. You can try that. You can take that in the sun, keep your paper, okay, and let all the sun's light pass through that. You will try to vary the distance between lens and the paper. You will get a perfect sharp, dark, white circle where all the sun's light will gather, and that will be the principal focus. Okay. So all the heat waves will be gathered at that point and they will cause burning of paper. Okay. So this is the ray diagram when the object is placed at infinity. You have is at infinity. Now a similar phenomena also observed with the concave lenses, and it is because of this reason that all the light rays they are converged at a common point. It is because of this reason that this lens is also called as a converging lens. We call this lens as a converging lens, as it converges, it collects the rays of light at a common. Okay. Next we see the diverging lens. Are you drawing the diagram along with Darian? Have you drawn the
No,
diagram?
sir. I'll do it, sir.
Okay, so try do the diagrams along the class only. Along with class, just keep your copy and pen, paper, draw the diagram. Okay. While
Okay,
drawing
sir.
the diagram, use your proper scale and pencil. Do not try to draw them with just your pen. Use your pencil, draw it.
Okay, sir.
Okay. Now see, you have a concave lens. Let's say we have a concave lens. This is our concave lens. It's also called as a diverging lens, and you can say it's thinner in the middle but thicker at the edges. At the edges, the lens is thick, but so I can again draw here a line passing through the midpoint, which we will call as the optic center. So here we obtain the optic center of the lens. So this is the optic center of the lens. Now here, this lens is the diverging lens. So if you have rays of light which fall parallel to the principal axis, so the rays of light, they do not actually meet, rather they appear to meet. Yes. So if you will have a ray of light passing parallel to principal axis, So here we take two rays which pass parallel to the principal axis. So the ray of light diverge from each other. The rays of light, they just diverge from each other. Okay. So they have diverged something like this. This ray of light, it diverges over here. This is how it diverges. So see, the rays of light which were coming parallel to each other, they have diverged. They have gone away from each other, and hence we call this as the diverging lens. Now, if you extend these light rays backward, if you try to pull the light rays backward, so you will observe that these light rays, they appear to meet at a common point. They are not actually meeting, they are going away from each other, but it seems as if they appear to meet at a common point. So here we can get them to be meeting at a common point. Okay. So this point where they appear to meet, they are not actually meeting, but they appear to meet. We call this point as the focus. So here, this one will be the focus, and we mark it as F1. See, the light rays, they were coming from the left side, and all the light rays, they come from the left side. They come from the left, and the focus is also on the left side. The focus and the incident light, they are in the same directions. Okay. So this is your diverging lens. Okay. So in your next class, I will be checking your ray diagrams for these two. I will be checking your three ray diagrams. That is one for the concave lens, one for the convex lens, and one for the glass lens. So these three ray diagrams you have to complete. I will be checking that through your camera only. Live, I will be checking.
Sir, those last two diagrams you drew, no, sir. Those and this one, no, sir.
Yeah, this one, this one, the last one, and the glass lens. This one. Okay. Okay. So bye everyone.
Sir, could you show once again?
Which one?
Bye, sir.
The second and third, sir.
You will find them in the PDF also. It will be available in the resource.
Okay, sir. Thank you, sir.
Okay, bye.